We're always trying to find the best way to do things, right? The fastest route to work, the most efficient way to pack a suitcase, the best deal when we're shopping. Well, it turns out there's a whole branch of math dedicated to exactly that. Today, we're diving into applied optimization, which is basically the art of using math to find the absolute best possible outcome in any situation. And trust me, it's a tool that shapes our world in more ways than you can probably imagine. So here's how we're going to tackle this. We'll kick things off with a classic puzzle I like to call the hiker's dilemma. Then we'll get into what applied optimization actually is, and I'll walk you through a sort of step-by-step recipe for solving these kinds of problems. After that, we'll see how this stuff pops up everywhere, from shipping packages to designing soup cans, before we zoom out and really appreciate the huge impact this all has. All right, so to really get a feel for what optimization is all about, let's just forget the heavy math for a second. Let's start with a story. It seems like a simple little puzzle on the surface, but it's a perfect example of the kind of tricky trade-offs we need to figure out. Okay, so picture this. There's a hiker at point P, and they need to get to a cabin over there. Now, part of the journey is along a nice, easy road where they can cruise at a solid 8 kilometers per hour. But to get to the cabin, they eventually have to cut through the woods, which is way tougher going. In the woods, their speed drops to just 3 kilometers per hour. So here's the big question. If the goal is to get to that cabin in the shortest possible time, where exactly should the hiker turn off the road and start heading into the forest? I mean, think about it. If you turn too early, you're going to spend way too much time slogging through those slow woods. But if you turn too late, you're basically taking the long way around. There's got to be a perfect spot, right? A best spot. Well, finding that perfect spot isn't just about making a good guess. It requires a formal, powerful tool designed for exactly this kind of problem. So let's actually define what we're working with here. And that tool is applied optimization. At its heart, it's really just a method for finding the absolute best value of something you care about, either the maximum or the minimum. For our hiker, we want to minimize travel time. For a business, you'd want to maximize profit. For a shipping company, you might want to maximize the volume of a box. It's all the same idea. And what's really key to understand is that every single one of these optimization problems has two fundamental parts. First, you've got the thing you want to optimize. That's your goal. For the hiker, it's minimizing time. And second, you've got the constraints. These are basically the rules of the game. For our hiker, the constraints are the two different speeds. If you're shipping a package, the constraint could be a size limit from the post office. You always have a goal, and you always have rules. So, how do we actually do it? How do we go from a word problem about a hiker to a concrete numerical answer? Well, it turns out calculus gives us this surprisingly straightforward 4-step recipe. Here it is, the whole game plan. First, you model the problem. You draw it out, you give things variable names, and you write one equation for your goal and one for your rules. Second, and this is where the magic happens, you combine those two equations into one single function. This is a crucial step. Third, you bring in the heavy hitter, calculus. You find the derivative of that function and set it equal to 0. This points you to all the potential best spots. And finally, you just verify which spot gives you the maximum or minimum you were looking for, and then you've got your answer. But hang on, why the derivative? What's that all about? Well, think of it this way. The derivative just tells you the slope or the rate of change of a function at any point. Now, if you're looking for the absolute highest peak of a mountain or the absolute lowest point in a valley, what's true about the ground right at that spot? It's flat. The slope is 0. So by finding where the derivative is 0, we're basically creating a treasure map that points to all the potential peaks and valleys. It's how we hunt for our answer. And once you have this recipe, you honestly start seeing optimization problems everywhere you look. It is absolutely not just for hikers in the woods. Let's run through a few more quick examples. Okay, think about shipping something. The post office might say that the length of your box plus the girth, that's the distance all the way around the middle, can't be more than 108 inches. So what are the perfect dimensions to give you the absolute biggest box possible that still follows the rules? That's an optimization problem. Or how about manufacturing? A company wants to make a soup can that holds exactly 16 cubic inches of soup. Simple enough. But what if the metal for the top and bottom lids is more expensive than the metal for the side? Optimization can find the perfect height and width of the can to hold the right amount of soup while minimizing the cost of the materials. Or let's get into some engineering. You've got a flat piece of sheet metal. At what angle do you bend up the sides to create a trough that can hold the maximum possible amount of water? Yep, you guessed it. That's another classic optimization problem. Now, these examples are all pretty cool.
But their rules, their constraints, are fairly simple. What happens when the rules of the game get way more complicated?
For that, mathematicians came up with an even more powerful tool called the Lagrange multiplier. Now, we're not going to get lost in the weeds here, but the basic idea is just brilliant. It's a method that takes a really difficult, messy problem with a bunch of complex rules and mathematically transforms it into a much simpler problem that we already know how to solve. It's pretty incredible stuff. So why does any of this really matter beyond these neat little puzzles? Well, because the ability to find the best possible outcome given a set of rules is, and I'm not exaggerating, completely fundamental to how our modern world actually works. I mean, just think about it. In economics, it's all about maximizing profit or minimizing cost. In logistics, it's finding the shortest, most efficient delivery routes. In engineering, it's about designing the strongest bridge using the least amount of material. This same thinking is at the absolute heart of modern finance, and even in how we train machine learning algorithms to be as accurate as possible. And this quote here, which is talking about those Lagrange multipliers we mentioned, really captures the sheer elegance of these tools. They give us a powerful, systematic way to handle really complex situations and find the best path forward, even when the rules seem incredibly tangled. So I'm going to leave you with this thought. Optimization isn't just some abstract concept from a math class. It's a way of thinking. So if you had this amazing mathematical toolkit and you could use it to perfectly optimize just one part of your daily life, your commute, maybe your budget, your workout schedule, what would you choose to make the absolute best it could possibly be?